Hello, everybody. Welcome back to Calculus. Now, at the beginning of this course, I mentioned that calculus can be classified into or divided into two major parts, one being differential calculus and the other being integral calculus. We are now at the transition between the first and the second halves of this course. So we move now from differential calculus to integral calculus as we enter chapter 5. In section 5.1, we will be studying what integration is all about, and that has to do with finding the area under the graph of a function. And so that's what we will study, the concept of the Riemann sum. And so that is what we are about to do in section 5.1, which is about approximating the areas under the functions. All right, so let's get started on section 5.1. All right, so you have a few graphs in front of you here. And so let's take a look at the first one. What I'm trying to do is to suggest to you how important it is actually to be able to find areas under the curve or under the graph of a function. All right, so at the beginning, we have the step function. You can see this, it's a step function, which is 50 miles an hour between 0 and 1, and then 70 miles an hour between 1 and 2. Now here, I'm thinking, of course, of driving for 2 hours, the first hour at 50 miles an hour and second hour at 70 miles an hour, right? The question is, what does the area under this graph of f, f is the step function with 2 steps, what does it represent? Well, if you look at the area here for the first rectangle, that's 50. And of course, the second is 70. And the total is 120. And of course, that represents the number of miles that you drove, right? No problem here. Okay, so I was thinking about all of these things as I was at the gym, which I try to do often. And you can be on the treadmill, and of course now the modern treadmills have all kinds of fancy tools in front of you. One of which is the graph of how much you have walked or run, right? And so they will indicate something like this even at the beginning before you start running. And let's say that this particular graph represents the miles an hour and the time. And now, normally the time is written in minutes, right? The first 10 minutes or first 15 minutes you run at this rate and so on. But because this is written or this is indicated using miles an hour, let's just assume that in this particular graph, I have the x-axis or the horizontal axis indicated in hours. So you have 0.3, which is what? 0.1 hour, meaning 6 minutes. So this is the 18 minutes, 18-minute mark. So for the first 18 minutes or first 0.3 hours, you were on the treadmill, you're running or you're jogging or you're walking really fast at the rate of 5 miles an hour. So this will be 1.5 miles that you ran or jogged or walked really fast for 18 minutes, right? The next, you have increased your speed. You increase your speed to 6 miles an hour. And again, for, well, let's see, this looks like 0.5 to me, right? So that's 3. Whoops, that's only, okay. So the width is 2, so that's 1.2 hours. So that's 1.2 miles that you walked or jogged during that 0.2 hour period, which is 12 minutes, right? Next, you have 0.3, which is 18 minutes. Next 18 minutes, that's 0.3 times 3, that's 9. You are basically walking at a rate of 3 miles an hour. And then at the end, you have 0.2 hours at a fast rate of 8 miles an hour. You are clearly running on your treadmill here. That's 1.6. So again, you can see that every rectangular area has to do with the miles you ran. And if you add them together, that would be the total distance that you were running on or walking on the treadmill, right? So the point here is that these areas actually mean something. And not only does it represent distance in these cases, of course, but depending on what that f of x is, the area under the curve is actually a relevant thing. Okay, it's going to give you some important, meaningful information in many applications. Now, typically, your speed will be changing a lot more frequently, and so it may look like this. Okay, but again, the total area, if this is miles an hour, and if this is let's say a 1 hour workout on the treadmill, and your speed is changing here, that's the step function, which is your f of x, right? And so the total area is again the distance that you ran on this treadmill, ran or walked or jogged. Okay. Now in reality, though, your function, the value of the function, unless you are on a treadmill or some artificial circumstance, your f of x is constantly changing. Like even when you're driving, it's very rare that you're driving constantly for for an hour at 50 miles an hour or 70 miles an hour. Your speed is constantly changing, more like this. Okay, so the same thing here. The area under the curve is going to be representing the distance traveled. Now, it's much more difficult when you don't have the step functions because you don't have rectangular regions, right? So how are we going to do this? And again, a little spoiler alert, what we will do is do exactly what we did in the first three examples. We're going to just assume that we have a bunch of these rectangular regions. Okay, so that means we will have to subdivide this interval, partition this interval into smaller subintervals, and then we sort of approximate the value of the function in that interval. And we, if the subinterval is small enough, you can assume that you are at the steady speed during that subinterval. And of course, the value of these, the value of the function at each subinterval is going to change. And somehow, if you can just add them, add the areas of the rectangular regions, then you would think that it's going to give you a nice approximation of the area, right? And that's exactly the idea of the German mathematician Riemann. And so that's what we will be doing. Now, notice here, before we can talk about this approximation, we'll be adding a lot of numbers, right? Here, we're adding 2 numbers. Here, you're adding 4 numbers. Here, you're adding lots and lots of numbers. And in fact, we will let this go to infinity. We're going to be adding sort of like infinitely many numbers if we can. Of course, we can't. So we'll have to depend on our concept of the limit, right? So the first thing, the area is important, okay, which is good because we'll be spending the this second half of our Calculus 1 class studying basically what amounts to the area under the curve, right? So before we get into it, though, I will introduce to you this sigma notation, and some of you may already be familiar with it, which is great if you are. And the sigma notation has to do with the capital sigma of the Greek alphabet, which looks like this. The lowercase sigma looks like this. It's like an O with a tail, but capital sigma looks like this. And this stands for the sum. And sometimes series, depending on the context. And these actually mean the same thing in mathematics. So what is the sum notation? What is the sigma notation? And maybe I should just tell you a story about this man named Carl Friedrich Gauss, right? Gauss was this German mathematician, sometimes called maybe arguably the most famous of all mathematicians, maybe the greatest of all. He is very, very well known. And so anyway, the story goes, and I don't know if it's true. Most people don't believe it's true, but it's nevertheless a great story. When he was like in first grade, his class of German children, they were quite noisy in the classroom, and the teacher, the female teacher, was very upset with the class, and she just basically shut up the class and told everybody to add all the numbers from 1 to 100. Natural numbers, of course, right? And of course, students were starting to add these, and nobody succeeded for the next hour or so, except this one little kid, Carl Friedrich Gauss, and he somehow figured out within minutes that the answer must be 550. And so, of course, the Fräulein, the teacher, says, "How did you do this?" And he said, "Well, you can just write all these numbers. This is what you had to do." And of course, what you would do, most people do, is to start adding from the beginning. That's 3, and that's 6, and that's 10. Next one is 15. It's going to take you a long time, especially as numbers get big. Okay, but Carl, the little Carl says, "Well, why do you have to do it this way? Maybe you can write these numbers backwards." Okay, what's the point of doing this? Well, because if you do this backwards, you have the 2 times the answer, right? You have 2 times the answer, the sum you want to find. And the advantage is each column is going to be 101, okay, right? Because you just added them backwards. So you have 100 of these, and that's twice the answer you want. So you just divide this product by 2, and you get 50/50. And of course, this is a very clever idea. Now, this is a great story, okay? I don't claim this to be true, but that makes a good story about Carl Friedrich Gauss. All right, so instead of writing all of these, and of course, you have to depend on these ellipses, because you can't, or you shouldn't be, well, you should not have to write all 100 numbers, right? So instead of this notation, we can use this sigma notation to indicate, hey, look, I am going to add numbers I. What do you mean by I? Well, I, we let that to be 1, and we let that range from 1 to 100. So this is the same notation that we are, this is the new notation, the symbol we are using to indicate this sum. Okay, so this would be exactly what I wrote. Okay, this is the first number, and this is the last number that goes on the top. These numbers are called index numbers or indices, and the sigma notation followed by what you are adding. Okay, so this is the sigma notation. Now I have just written this. Okay, it doesn't matter what you call this, right? So you can call this J. J is often used as an index. That's the same thing. Or you can actually make a little change. Let's say K plus 1, okay? And K goes from 0 to 99. And if you think about this, if you list all these numbers, K plus 1, as K goes from 0 to 99, you will get exactly the same sum. And of course, the sum is 5,050, as we just saw. All right, so that's this new symbol that we are learning. Let's just practice a little bit. Many times we don't even know what these numbers are. So we will just use an algebraic expression with an index number like that, okay? So what does it mean? S sub I added together as I goes from 1 to 5. If you write this in a traditional way, this is S1 plus S2 plus S3 plus S4 plus S5. Okay, that's what that means. Let's try another one. How about this? 1 over J square as J goes from 2 to 4. Okay, you see what that is? This is 1 over 2 square plus 1 over 3 square plus 1 over 4 square. Okay. And I don't want to calculate this. I'm just teaching you how to write these things. Okay. If you have infinitely many terms, that's okay too. Right. So for instance, you can do this 1 over 2 to the kth power as k goes from 1 to infinity. And so this means, again, it's an infinite sum, which is called an infinite series in mathematics. When k is equal to 1, that's the initial summand, and that's 1 over 2. And next you have 1 over 2 squared, which is 1 over 4, 1 over 8, 1 over 16. And the idea is this one never ends. And you say, well, that's silly. How do you add infinitely many numbers? Okay, well, it turns out there is a way to define this. And in this case, it actually becomes a very finite number, which is 1. Okay, so with this summation notation, I'm going to list some of the fundamental or very basic or intuitive results, okay? And so you can call these sigma rules if you like. First, tell me what this is. If you have C, this actually may be confusing, okay? What does this mean? Because there's no index here, right? Every one of these, you had some index so here's an index, and this one does have some reference to the index, right? Even here, you had the index appearing in the each of the terms. So here, it's C, a constant, added as I, which doesn't exist here, from 1 to n. All this is saying is, when I is 1, you have C. When I is 2, you have C. When I is n, you have C. Basically, you just add C n times. And so, of course, this is n times C. All right. Next, we have C times AI, where I goes from 1 to n. So this is C times A1 plus C times A2 and all that. The last one is C times AN. And of course, you can factor out C from all of these terms. So the answer here, assuming that the sum exists, of course, is this, which is C times the sum. So all this is saying is that the constant can be taken out of the summation notation. All right, and then the next one, if you have the sigma of AI plus BI or AI minus BI, you can probably guess what this will be, right? Because if you have A1 plus B1, and then A2 plus B2, and then A3 plus A3, and all the way here, it's possible to rearrange the order of your addition and get all the A's first, and you can add up all the B's next. It should not matter because you're talking about finite sums, and these things do exist, right? If it's minus, you put the negative sign. So that is, this basically says the sum after a sigma notation, the sum works like the limits and the derivatives. Remember, we learned that in chapter 2 that the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits. In chapter 3, we learned that the sum of the derivative of a sum is the sum of the derivatives, and so on, right? So what does this say in English? Wait for it. Ready for it? This one says the sum of a sum is the sum of the sums. Say that with me again. The sum of a sum is the sum of the sums. The sum of a difference is the difference of the sums. Wow, okay. All right, number 4. If you have AI added from 1 to n, this is the same as, let's say you go from 1 to some number m, and then you start from m plus 1 to n. And of course, here, I am assuming that m is between 1 and n. Okay, so let's just have this here. Okay, and in fact, let's not have this here either. All right, so again, if here, you're adding the first n terms, but you can stop at any point here, and then you can continue with the subsequent term, right? So that's, really, these things are obvious. Now, of course, these, we call these, and this is a theorem, a set of statements called a theorem. And of course, that means there are proofs, but the proof is actually not so difficult. And they're pretty intuitive and obvious, right? So we will not worry too much about this. All right, so in studying this, we have 2 special things I want you to know, 2 special sums. We have already established this, okay? But if you have numbers added from 1 to n. So this is what we're talking about. The sum is all of these. Okay, this is what Gauss did when n is 100. You can also write the sum backwards. All right, and then you can add vertically. 2 times the sum you want is n plus 1, n plus 1, n plus 1 added together, and you have, of course, n columns. So that's n, right? So this gives us the solution for this sum S, which is n plus 1 all over 2. Okay, and so that is it's basically called a geometric series. Sorry, it's called an arithmetic series with the difference of 1 between these two numbers added, two consecutive numbers. All right, I said two special sums. That's number 1. The second one is a little more challenging. And by the way, there are ways to prove these. Number 1, this is basically the proof, but you can use this fancy technique called mathematical induction to prove both of these, right? The second one is the sum of the first n positive integers squared. All right, so this will be something like 1 square plus 2 square plus 3 square plus 4 square plus blah 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 n squares. Okay, that's what this is. And basically what this is, you have to, I am not going to require you to know this, but just remember that there is this formula. It's n times n plus 1 times 2n plus 1 all over 6, right? And you can check and see this. You can verify this for yourself for any n, which of course doesn't prove it, because to prove this, you have to say that this is true for all n. That's infinitely many cases. And so in order to prove this once for all, you need something more than just finding a few examples. You have to use something like mathematical induction to prove that. Okay, so how does this relate to, and how is this used in approximating the area under the curve? That will be covered in the second part of this video.